Welcome to DCE Digital Learning Session. I am Shobhan Kumar. Today we have to discuss isomorphism of rings. Already you know the definition of rings, subrings, ideals and homomorphism. Isomorphism of rings. Definition. A mapping F from R to R dash is said to be isomorphism if F is homomorphism. That is, f of A plus B is equal to f of A plus f of B, and f of AB is equal to f of A, f of B for all A and B belongs to ring R. With this, f is 1, 1 and on 2. Then we say that R is isomorphic to R dash, and we denote symbolically by R is, we can write the symbol, it means isomorphic to R dash. R is isomorphic to R dash. Examples. Let z plus dot be the ring of integers. Now define f from z to z by f of x equal to x. For all x belongs to z, then f is homomorphism. Here we define the mapping f from z to z by f of x equal to x. Then show that f is isomorphism. Solution. First you have to prove that f is homomorphism, f is 1, 1 and f is onto. If any one of the condition is not satisfied, means f is not isomorphism. First we have to check whether it is homomorphism or not. Consider f of x plus y is equal to, here x and y belongs to z, implies x plus y is also element of z because z is a ring. Therefore, f of x plus y is equal to x plus y. Here define f of x equal to x for all x belongs to z. Therefore, f of x plus y is equal to x plus y. That is equal to x can be written as f of x and y is f of y. Therefore, f of x plus y is equal to f of x plus f of y. And f of xy is equal to xy. That is equal to x is f of x and y is f of y. For all x and y belongs to z. Therefore, f is homomorphism of z into z. Now we have to prove that f is 1-to-1 mapping. By definition of 1-1 mapping, now consider f of x equal to f of y for all x, y belongs to z, implies by definition f of x is x and f of y is y. Therefore, x equal to y. Therefore, f of x is equal to f of y implies x equal to y means f is 1-1 mapping from z to z is 1-1. Next, we have to prove that f is onto. Here from this mapping, let x belongs to f of z be an arbitrary. This is arbitrary element in f of z under this mapping. Then there exists x belongs to z such that f of x equal to x. Therefore, f is onto. Here f is homomorphism, f is 1-1 and f is onto means thus f is isomorphism from the ring z into itself. Another example. Show that z plus dot be the ring of integers and 2z plus dot be the ring of even integers. Define mapping f from z to 2z by f of x equal to 2x for all x belongs to z. Then f is not isomorphism. Here already we know that the definition of isomorphism is f is homomorphism, f is 1-1 and f is onto. Now I have to verify one by one. First I have to check it f is homomorphism or not. If it is homomorphism, next we have to check f is 1-1 and onto. If not homomorphism, we can stop that stage and we conclude that f is not isomorphism. Consider two arbitrary elements 2 and 3 in z. Then f of 2 is equal to 4 because f of 2 is equal to 2 into 2. Here by definition in the problem is given f of x equal to 2x. Therefore f of 2 is equal to 2 into 2 is 4. F of 2 is 4 and f of 3 is equal to 3 into 2 or 2 into 3 is 6, then f of 2 into 3 is equal to f of 6, that is equal to 2 into 6 is 12. But f of 2 into f of 3 is equal to 4 into 6 is equal to 24. This implies f of 2 dot 3 is not equal to f of 2 dot f of 3. Therefore, f is not homomorphism and hence f is not isomorphism. Next example. Let z plus dot be the ring of integers and 2z plus star be the ring of even integers, where star is defined by a star b is equal to ab by 2. This is ordinary multiplication, usual multiplication, but this is an operation. Star is an operation defined like this. A star b is ab by 2. For all a and b belongs to 2z, define mapping f from z to 2z by f of x equal to 2x. For all x belongs to z, then f is an isomorphism. Here we have to prove that f is isomorphism. First, we shall show that f is homomorphism. Here, by definition of homomorphism, consider f of x plus y is equal to, here f of x equal to 2x. According to that, f of x plus y is equal to 2 into x plus y implies 2x plus 2y, that is equal to f of x plus f of y. Therefore, f of x plus y is equal to f of x plus f of y. And f of xy is equal to 2xy by definition. And consider f of x star f of y is equal to 2x star 2y. 2x star 2, it is like a star b. Here 2x into 2y whole divided by 2, that is equal to 2 to get cancelled, remaining 2xy. Therefore f of xy is also 2xy and f of x star f of y is also 2xy. Implies f of xy is equal to f of x into f of y. Hence f is homomorphism. And remaining to prove that f is 1, 1 and not 2. If x and y are any two elements of R, then consider f of x equal to f of y. Implies f of x is 2x and f of y is 2y. 2 to get cancelled, that is x is equal to y. Therefore f of x equal to f of y implies x equal to y, means f is 1, 1 mapping from z to 2z. Also f is onto for if there is an even integer in R dash, then it is of the form 2x for some integer x, and therefore it is the f image of an integer x in R. In R. And another example, let R plus dot be the ring of all complex numbers. R dash be the ring of all 2 cross 2 matrices of the form AB minus BA, where A and B are real numbers with respect to matrix addition and matrix multiplication. Define mapping F from R to R dash by F of A plus IB is equal to matrix AB minus BA. Verify whether F is homomorphism and an isomorphism. Find kernel F. Solution. Let x comma y belongs to R, where x is equal to a plus ib. Here x and y are complex numbers. X is equal to a plus ib and y is equal to c plus id. First we have to prove that f is homomorphism. Therefore f of a plus ib is equal to, here by definition, here define f of a plus ib is equal to matrix ab minus ba. F of a plus ib is equal to ab minus ba, and f of c plus id is equal to cd minus dc. Now consider f of x plus y is equal to, x is a plus ib, y is c plus id. Substitute here. That is equal to, according to this definition, before that it can be written as f of a plus c plus I into b plus d, and then using this definition We get matrix A plus C, B plus D, minus of B plus D, A plus C. And again it can be written as here AB minus BA plus CD minus DC, that is equal to, this is f of A plus IB plus this is f of C plus ID, that is equal to f of x plus f of y. Therefore, f of x plus y is equal to f of x plus f of y. And f of xy is equal to, here x is a plus ib and y is a c plus id. F of a plus ib into c plus id, that is equal to f of a after multiplication and simplify. We get ac minus bd plus I into ad plus bc. And again using the definition, we get AC minus BD, AD plus BC, minus of AD plus BC, AC minus BD. And again it can be written as AB minus BA, CD minus DC, that is equal to f of x into f of y. Therefore, f of xy is equal to f of x into f of y, implies f is homomorphism. F is 1, 1. Let x equal to a plus ib and y is equal to c plus id belongs to ring R. Therefore, f of x equal to f of y implies f of a plus ib is equal to f of c plus id. This implies, we know the definition of f of a plus ib and f of c plus id, that is equal to ab minus bd a, sorry, that is equal to matrix cd minus dc, implies these two are equal matrices if and only if A is equal to C and B is equal to D. B is equal to D. A is equal to C and B is equal to D. This implies A plus IB is equal to C plus ID. That is x is equal to y. Here f of x is equal to f of y implies x is equal to y, means f is 1, 1. And f is onto. Let's consider one arbitrary element in this form in R dash. Then there exists A plus IB belongs to R such that f of A plus IB is equal to matrix AB minus BA, implies f is 1, 1 and onto. Here it means f is onto. Thus f is homomorphism 1, 1 and onto. Therefore f is an isomorphism. Now I have to find kernel of homomorphism F. By definition of kernel F is equal to x belongs to R such that f of x equal to 0. That is equal to, here already we define x is nothing but a plus ib, complex number in a ring R. A plus ib belongs to R such that f of a plus ib is equal to 0. That is equal to a plus ib belongs to R. By definition, f of a plus ib is the matrix AB minus BA, that is equal to, this is a zero matrix, zero element in R dash, that is a zero matrix, 0, 0, 0, 0. That is equal to a plus IB belongs to R. Here if these two are equal means A equal to 0 and B is equal to 0. And again here substitute here 0 plus I0, that is equal to 0. Therefore kernel F is equal to 0. Next, properties of isomorphisms. Theorem: if F from R to R dash be a isomorphism of rings R into R dash, then if R is commutative ring, then R dash is also commutative. If R is without zero divisors, then R dash is also without zero divisors. If R is a ring with unity, then R dash is also with unity. If R is an integral domain, then R dash is also an integral domain. If R is a field, then R dash is also a field. If R is a division ring, then R dash is also a division ring. Now we have to prove one by one. For proof, first one. Here we have to prove that R is commutative ring implies R dash is also commutative ring. Consider two arbitrary elements in R dash. Here A dash B dash belongs to R dash implies A and B belongs to R such that f of a is equal to a dash and f of b is equal to b dash because mapping f from R into R dash. Consider a dash b dash is equal to f of a into f of b, that is equal to f is homomorphism. It can be written as f of ab. That is equal to, we know that R is a commutative ring and a comma b belongs to R. Therefore ab is equal to ba. Therefore f of ab is equal to f of ba. And again f is homomorphism. F of ba can be written as f of b into f of a. That is equal to, by definition, f of b is b dash, f of a is a dash. Thus a dash b dash is equal to b dash a dash. It means R dash is also commutative ring. Therefore if R is commutative, then R dash is also commutative. Next we shall show that a dash b dash is equal to 0 dash in R dash implies a dash is 0 dash or b dash is 0 dash. Any one of them should be 0. Let us consider two arbitrary elements a dash b dash in R dash and a dash b dash is equal to 0 dash. Since a dash dot b dash belongs to R dash, sorry, a dash b dash belongs to R dash, implies there exists a b in R, a and b in R, such that f of a is equal to a dash and f of b is equal to b dash. Since f is onto mapping, f is onto mapping. Now consider a dash into b dash is equal to 0 dash implies, we know that a dash is f of a and b dash is f of b, that is equal to 0 dash is f of 0. This implies f is homomorphism. It can be written as f of ab is equal to f of 0. This implies ab is equal to 0 because f is 1 1. AB is equal to 0 implies either A is equal to 0 or B is equal to 0. Since R is without zero divisors. Without zero divisors. Therefore, f of A is equal to f of 0 or f of B is equal to f of 0. Here f of A into f of B is equal to f of 0 implies either f of A is equal to f of 0 or f of B is equal to f of 0. That is a dash is equal to 0 dash or b dash is equal to 0 dash. Therefore R dash is without zero divisors. That means if ring R without zero divisors, then R dash is also without zero divisors. Next one. Here if R is a ring with unity, then R dash is also a ring with unity. Let R be a ring with unity, then f of 1 belongs to R dash. Here 1 belongs to R, under the mapping f of 1 belongs to R dash. Let A dash belongs to R dash implies f of A is equal to A dash for some A belongs to R. Now f of 1 dot A dash is equal to f of 1 A dash is f of A. F is homomorphism. Thus f of 1 dot f of A can be written as f of 1 dot A, that is equal to f of A, that is equal to A dash. Here 1 dot A is A itself, since 1 is a unit element in a ring R. A is also belongs to R, 1 is also belongs to R. Therefore 1 into A is A itself. F of A is equal to A dash. F of A is equal to A dash. Similarly, A dash into f of 1 is also A dash. Therefore, R dash is a ring with unity f of 1 because A dash into f of 1 is equal to A dash means f of 1 is unit element in a ring R dash. Next proof. Here, if R is an integral domain, then R dash is also an integral domain. That means if R is an integral domain, then we have to prove that R dash is also integral domain. Already you know definition of integral domain. Integral domain is a commutative ring with unity which has no zero divisors. We have to prove that the ring R dash is commutative with unit element and has no zero divisors. Let R be an integral domain. Then R is a commutative ring with unity and without zero divisors. We have to prove that in 1, 2 and 3 earlier cases. R dash is also commutative ring with unity and without zero divisors. Therefore, R dash is an integral domain. And the fifth one, if R is a field, then R dash is also a field. Just using the definition of field. Okay, here field is a commutative ring with unity in which a very non-zero element has multiplicative inverses. Here we have to prove that non-zero elements in R dash possesses multiplicative inverse. Okay, let R be a field. Then here by definition of field, then R is a commutative ring with unity and a very non-zero elements as multiplicative inverse. This is a definition of a field. It is already established that R dash is commutative ring with unity. It is enough if we show that a very non-zero element in R dash has multiplicative inverse. Now consider non-zero element in R dash. Let A dash belongs to R dash be a non-zero element. Then there exists a non-zero element A belongs to R such that f of A is equal to A dash. Since R is a field and A is non-zero, therefore A inverse exists in R and f of A inverse exists in R dash under the mapping F. Here A inverse belongs to R, then f of A inverse belongs to R dash. Now consider A dash into f of A inverse is equal to A dash is f of A and f of A inverse is f of A inverse. That is equal to f is homomorphism from R into R dash. Therefore f of A inverse, that is equal to A inverse is 1. F of 1. Similarly f of A inverse into A dash is f of A. Therefore f of A inverse is the multiplicative inverse of A dash or f of A. Hence R dash is a field. And finally we prove that if R is a division ring, then R dash is also a division ring. We know that every field is a division ring. Division ring or skew field. In proof 5 implies that R dash is a division ring. And these are the exercise problems you can do yourself. And these are the reference. Thank you.